Hello everyone and welcome to the first part of this week's lightweight Java game library 3D game tutorial. This week the tutorial is split into two episodes, one today and one on Saturday, just because it was a bit too long for one episode. So we're going to be learning about shader programs today, and then in the tutorial on Saturday we'll actually be coding some. There's no actual programming in this tutorial, so if you're already pretty confident that you know what shaders do and how they work, then you can just skip this tutorial and do the one on Saturday. But if you've never worked with shaders before, then I definitely recommend that you watch this video to get an idea of what we'll be working with in the next episode. So when you run your game, a lot of the processing is done on the central processing unit of the computer. Things like the game logic, calculations, and all the gameplay that you might implement are all carried out and processed by the CPU. However, when it comes to rendering the scene, like when we call GL draw elements, the graphics processing unit comes into action. The GPU renders your objects to the screen, and it also determines exactly how they're displayed. For example, it determines whether they have a color, whether they're textured. It can also change the position and scale of the object on the screen. It can calculate how objects are affected by lighting, by shadows. It can add fog effects to the objects. All of this visual stuff is dealt with by the GPU. Now, in the old OpenGL, with the fixed function pipeline, you had a finite list of functions that you could use to tell the GPU how to render your objects. You could basically just tell the GPU to do certain things to your objects, like make it a certain color, add a light here, make it foggy, give it shadow. Obviously that's a bit simplified, but it was a lot easier to achieve these effects, but also very limited indeed, and it didn't give the developer much room for maneuver. Now, however, with the modern programmable pipeline in OpenGL, these fixed functions are gone, and we can program the GPU ourselves to program it exactly how we want it to render our objects. This does mean that we have to create things like lighting functions and such ourselves, but we now have total flexibility. And these programs that we create that run on the GPU are called shaders, and we're going to be writing them in the OpenGL shading language GLSL, which as you can see is pretty similar to Java, and it's really easy to learn. So how does a shader program work? Well, there are two types of shaders that we have to program that work together to render a scene, and they are the vertex shader and the fragment shader. The vertex shader executes one time for each vertex in the object that's being rendered, and each time it uses the vertex data that we stored in the object's VAO as the input to the vertex shader program. So in our game at the moment, we only store positional data about each vertex in the VAOs, so the input to our vertex shader would simply be the XYZ coordinate of the vertex that was currently being processed. And we have to make the vertex shader do two things with this data. Firstly, it has to determine the position of where the vertex that it's processing should be rendered onto the screen. That will be really easy for us because the vertex position that we get as the input to the vertex shader is already the position where we want to render the vertex on the screen. But this won't always be the case in the future, and so we'll have to program some calculations in the vertex shader to convert it. Secondly, the vertex shader uses the input, executes the program, and outputs something. These outputs can be anything, whatever you program them to be. It could be two floats, a 3D vector, three floats and a 2D vector, or any combination of floats, vectors, and matrices. These outputs are only used as inputs to the fragment shader, so you choose what you need them to be. Let's say, for example, that we program the vertex shader to convert the position that it got as an input to a color for each vertex, an RGB value for every vertex that it processes. So let's say that when the vertex shader ran on this vertex, it outputted this RGB value of 000, so black. And then for this one it outputted 001, and for this one it outputted green, and for this one here cyan. And these colors are then only used as the inputs for the fragment shader. Now the fragment shader executes one time for every pixel that the object covers on the screen, so that's quite a lot of times. Each time it runs, it uses the output of the vertex shader to calculate what the final color for that pixel should be. So the output of the fragment shader is always an RGB color, the color of the pixel that is being processed. But what would the input to the fragment shader be in our example here? I've already said that the output of the vertex shader program was an RGB color, and that the inputs to the fragment shader are always the same as the outputs of the vertex shader. So the fragment shader program in our example must use an RGB color as its input. But which colour should the input to the fragment shader be when it processes this pixel here, for example? There are 4 vertices with 4 different colours in the model, so which of these colours should the fragment shader use? And what about when it processes this pixel, or any of the other pixels? How does the fragment shader decide which colour it should use as the input to the program? Well, actually, for each pixel that the fragment shader is executed for, it uses a mixture of the vertex shader outputs for the 3 vertices that make up the triangle which the pixel is in. And the vertex values are linearly interpolated depending on their distance from the pixel. So that means that the amount that each vertex value affects the input value of the fragment shader for a certain pixel depends on how close the vertex is to that pixel. So when the fragment shader executes for a pixel right next to this vertex, the input color is going to be almost entirely black because that vertex's output from the vertex shader was black. A pixel halfway between the black and the blue vertices would have an input color that is halfway between black and blue. And a pixel over here would have an input that is pretty much an equal mix of these 3 vertices colors. So for pretty much every pixel, the fragment shader will use a slightly different input. It then processes this input in whatever way we program it to, and from this it calculates the output color of each pixel, which would look possibly something like this, but probably nicer because it won't be done in Microsoft Paint. And it's important to note that to render this rectangle, the vertex shader will have to execute 4 times, once for each vertex, while the fragment shader will execute once for each pixel, which for this rectangle would be something like 10,000 times. So let's quickly recap all that, because if you've never heard of shaders before, that was probably quite a lot to take in. So the vertex shader program is a program that we write, and it's executed once for every vertex in the model that we want to render. It uses data from the model VAO to first determine where on the screen the vertex should be displayed, and then calculates and outputs some per vertex variables. So let's do a different example now and say that we've programmed the vertex shader to output 2 float values, one called cat factor and the other called dog distance, because why not? So after the vertex shader has run for every vertex in the model, all of the vertices will have a cat factor and a dog distance value. So now the fragment shader executes once for every single pixel within this model. And as we know, the input to the fragment shader is the output from the vertex shader. So each time the fragment shader program executes, its inputs are a cat factor and a dog distance. So let's say the fragment shader is executing for this pixel here. The inputs to the fragment shader for this pixel will be a mixture of the 3 outputs of these vertices, each one weighted depending on its distance from the fragment. And this is done automatically by OpenGL. So this pixel here would have a cat factor of about 26.2 and a dog distance of like 0.6. And we'll have programmed the fragment shader to use these inputs in some way to calculate the output color of that pixel, which let's say in this instance turns out to be green. And a different pixel would have a different cat factor and dog distance values, which would lead to a different color being outputted. And the fragment shader does this for every single pixel to calculate all the pixel colors for our model. So that was just a very quick and very simplified explanation of how shader programs work, but hopefully it will be enough to give you a basic understanding of what's going on when we program some shader programs for ourselves on Saturday. But that's it for this tutorial. Thank you guys very much for watching. Do subscribe if you haven't already. Have a lovely rest of the week, and I will see you all on Friday for the devlog and then Saturday for the next part of this tutorial.